Hello everyone. Come back again to the class. Sorry for like one couple of days delay for this video. Simply because I cannot manage my own schedules to produce the content for you guys quickly enough as I can. However, I would like to first of all telling you guys the fact that what the class is going to be and about the scoring and the grading system. So for this class, we already have couple of assignment. I'm gonna give some more, and we still have times until 20 of July for almost sum up everything, and then I can sending the grade as late as possible around 25 or 26 of July, and then everything gonna be okay for all of you without have to be worried that the grade gonna be postponed to be announced in next semester or whatsoever. That's what I want to make clear here, that the delay will not cause any effect on your transcript. I already consult with the dean of CPE, so that's gonna be fine. Also, the other thing that I would like to mention is that some of you worry about how we can calculate the grade. I mean the grading policy and the criteria. I already consult with the CPE, and we can judge you mostly on the competency of how you understand the importance of data structures and how you select each data structure itself more than coding. So that's why in most of the assignment I trying to focusing on pseudocode, on flowchart, or anything more than the coding, because in the end of the day, most of this data structure right now can be downloaded as libraries and instantly use it. But you need to understand in which application that you're going to use which type of data structure to produce either faster computational times or more effective algorithms respectively. So that's why I would like to start mention the application of each data structure itself much more. And in the past, I tried to compare linked list and array in couple of application, either when you implement it to be stack and queue, which one is going to be better in which kind of circumstance. Especially if you look at searching and sorting, it's going to make more sense that okay, in some kind of searching algorithms it's better to use array, in some kind of searching algorithm you need to use linked list, or either combination of both to make it more effective. So it's gonna be harder question to understand for trees. For me, when I was student as well, like I don't understand like why we need the tree structure. I didn't see it's gonna be kind of effective in most of the circumstance. So what I would like to mention here is one of the kind of application of trees that make me realize that okay, this one is makes sense, and this one is gonna be perfect example to implement in Trie, and only most effective on the Trie itself. So I would like to show the Google search system. So I don't know about you guys, but in the past, when I was young, we didn't have this kind of good searching search engine yet. In the past, we have like some competitors between Google and Netscape and blah blah blah. Especially Microsoft try to play around in this market as well. In Bing right now, not many people heard about it. And one day Google come up with this feature that whenever you type something in, and then you're gonna see like whenever I type anything, either it's gonna be wrong or correct, then it's gonna come with the list of suggestion of word one by one. If I remove some, it's still like suggest that it's going to be agency, agenda, agent, or whatsoever. How is come up with that? It's so fast. You can look at it. It's like and it's not depends on your internet connection that much. So even though you have pretty slow internet access nowadays, whenever you type anything on Google, the suggestion will come extremely fast, in extremely fast pace. And in the past, like as a student, I don't really know like Agent of Shield whatsoever. Like as a student, I don't really know how to implement it. I feel like, yeah, that's so cool application. And we imagine that, okay, because Google have like extremely large computational power, large data center, so they can produce this. Until I went to the class, it's in the past, it's kind of like joint class between CPE and University of Washington. We have one invited speaker came from Washington DC and teach us for one semester. And then it turned out that this feature can be implemented on laptops and didn't use much of computational power at all, but it resolved by the Trie data structure. Even though, like in the end of the day, Google call it trees, but write down like this. The full name of the structure, like that they propose at that particular moment of time, is called effective retrieval structure, and it's implemented based on Trie structure. That's why they just like cut down like the middle word here to kind of like play around. It's like a word play. Like when you call trees, it's gonna be either like those tree data structure or trees that is a new data structure that proposed by Google. Okay, so how it work? For example, like we have this pool of word. We have like 6 words here. Okay, then we want to be able, like whenever we type A, then they will have some suggestion of word came along. And whenever I typing it a little bit more, the suggestion of word is going to be changed by the prefix. We call, like in the linguistic, the prior part of the word that we type. For example, like I've typed only A right here, like A, G, for example, here, and then later on I'm gonna type something down, but here is what we call prefix, and then it's gonna be follow up with couple of different words, couple of different syllables, can be whatever alphabet later on that is gonna make it to be word in dictionaries. So the way it works is that, okay, we know like from several prefix, if you know some alphabet and conclude it to be one prefix, you can guessing the syllable. It's like your word game in the past. Like if I'd say like A, the word start with A and G, and then it have only 3 alphabet, then you can make the guess, right? It's either gonna be age or I cannot come up with another word. But then if we have 6 alphabet for starting with A and G, it's gonna be like agenda, agency. Yeah, I have like, I'm really blank about vocabulary. Anyway, but that's the kind of idea that the algorithm itself should work and can be able to play these kind of word games, because you want to type some word in and then let it guess for you what is the next alphabet for that particular word that you're searching for. So the way the machine learn this data structure should be constructed by the fact that you're gonna type down each alphabet one by one. So you should gain that benefit in your mind. Then from now, right here, I would like you guys to pause the video and try to think. I hope you're gonna come up with some idea that close to the real algorithm. But then if you cannot do that, it's okay. Okay. I'm gonna show the sign, and please pause the video, and whenever you run out of solution that you can imagine in mind, or you have any kind of solution that you can thinking of, then start the video again to see that is close to the solution that I've proposed, which is the same with Google or not. Okay, please pause it here and come back whenever you want to. Okay, come back to the class. So the idea that you're gonna have one big pool of word in dictionary feed in, and the machine gonna learn and construct one data structure that gonna be used only for retrieve the word, as I mentioned like before. So the way it works is split each word into the list of alphabet. So all of them is gonna be like A, G, N, G, B, B, S, E, T, and what so on. So each word gonna be split into each particular alphabet, and then it's gonna put into the learning algorithms that gonna construct a tree. And the tree, these specific trees gonna start with a root of nothing. So the root is gonna be null. It's gonna start with nothing because at the searching circumstance, searching scenario, you start searching from nothing, right? So most of the case, you start the search from nothing, not doing anything, and then each word that feed in to the system gonna be construct the children node of the root. So for example, if we feed the first alphabet from this pool into this algorithm, the root is gonna be null. And then from root, what happened is it's gonna learn the first alphabet. So first of all, it's gonna learn from the first word, agenda. So next from root is A. Okay, so that's gonna be the look of the trees after they learn the first word, agenda. So it's simply gonna construct the child node one by one for each alphabet that they learn. Then what else they're gonna do is they're gonna feed the second word. Okay, right now we learn the word agenda. Oops. Okay, then next word is gonna be ant. So when ant feed in the system, what happens is it's gonna search through these trees, okay, and see how far it can go without any unknown happens. So what happened is the first alphabet from root is going to be A. So they search for the child node that have A value inside. If they have A on that, then they jump to the next alphabet, which is N. So they search that the child node of A has N or not. Right now it has only G alphabet, right? So without N, they're gonna construct the new node under the first one that they cannot find. The child, and then they construct the next node, which is T here. Then the new word come in, and then we transfer in the tree again. So it's going to be A from now to A to G, E, N, and from now we didn't have C. So it's going to construct the other node here. We keep continue this process, and then at the end your trees will look like this. Okay, so at the end, after you learn all the vocabulary here, the tree is gonna look like this, and you're gonna see like the way I draw it. Even though it's not like good drawing, I'm gonna start from the left and expand to the right, because the algorithms here to construct the node is called left node insertion. So the first word that you feed in, you're gonna feed at the left hand side to be the child node on the left of each master node. For example, like from A to G, G is the first one, then I'm gonna construct it on the left. And then whenever we found the next child node from the vocabulary that we learned, we're gonna construct on the right hand side of the previous child node. Okay, so this here not gonna arrange by the alphabetical order. It's not gonna be like that. It depends on the list of vocabulary that you learn in internet. And you can imagine, like as Google, they have the big pool of wording that people keep searching on the internet. They just memorize the word, send it in database, don't care how much people are gonna type the same word in the same days. And they construct these trees by the history of data that they learn in that day. So at the end of the day, they're gonna have one big trees that construct based on the searching word. And whenever users type A, then they can make like quick transfer between each branch of the trees, and then making list of suggestion word following that. Like whenever I type A, and then it might be like G and B following that, like either the word agenda and an abstract. However, when I type A and then following by B, then the list of suggesting word is gonna be narrowed down to be just abstract or abdominal. Okay, or if I change it to be A and G, then they will just travel until they see another branch in the structure. So they're gonna be like A. When I type AG, it's not gonna suggest E. It's gonna suggest either agenda or agency. So you can see like how many this data structure gonna be more flexible in terms of the word suggestion, depend on how many words that you feed to them as a learning algorithms. Okay, so you can imagine how fast it's going to be using for retrieve data. For learning, it's going to take time, depending on the way you write down the algorithm itself. This is just one of the example that you can do is a left node insertion algorithms, but they have couple of variation of trees construction. However, when we retrieve the data, like when we type word and want it to retrieve the list of suggestion word from the structure, computational time is gonna equal to the length of the word, simply like that. Because whenever you type each word, they're gonna search for the next suggestion immediately. They can put all the suggestion of word immediately, because you can see like from this data structure, they just see like, okay, you type which alphabet in and what is the prefix before that. Then whenever you type any word, they just travel along this data structure one by one and travel until the end of each node to get the suggested word. So it's going to be extremely fast. In the future, when you learn how to compute computational times, it's not just computational time, it's called computational complexities, which is can be calculated in terms of big O. So whenever you look at the big O of the data structure, it's going to be equal to M, which is the length of the word, which is simply extremely fast traveling times or retrieval times for this data structure. And as you can see, this fantastic idea cannot happen if we didn't have the idea of simple tree structure in the past. So if we don't have this simple tree structure in the past that we implement into binary search tree, then the researcher in Google didn't come up with this idea at all. So they implement this one because, okay, from the tree, which is common data structure, easy to implement, but we didn't have much of application of it. We just expand it from binary to be many to one trees, like from single root of node from now, and then you expand it into like 26 alphabet in English, and then next word and so on. You can construct the same kind of trees in every single languages in the world. That's the fantastic point of this data structure, because you break it down into the way people type each alphabet in that languages. So even for Thai languages, you can start from Sara A and then follow for each alphabet, and then you follow by the tonation marker, which is Vanayuk. You're gonna follow, and then you follow by another alphabet or whatsoever. You can do the same thing with every single languages in the world for this data structure, and it's very effective. Yeah, that's the kind of application that I want to show you today, that trees can be very effective. Depends on the way you implement it and the algorithm that you're gonna use with it. Okay, and then from my example of tree structure, I would like to again give an assignment. That's gonna be a good cumulative score that we're gonna use for do the grading. The thing that I would like to ask you to do today is to construct the flowchart or pseudocode for tree construction. For some of you who want to implement it to be the code, that's fine. But I'm happy enough if you have the correct pseudocode or flowchart. If you want to construct the code, or you get things stuck of how to implement the trees, you can consult me as a separate like kind of consultant under the comment below in Facebook group, or either in my direct message. But I would like it to be the group like the discussion in public space, like in the Facebook group, because like your friend gonna be able to see it and follow up with your question and get some idea back as well. Okay, so the idea is all the input is gonna be English words or phrase that already split into the list of alphabet and special characters. Why I include special characters? Because in some word, like when I'm searching in Google searching box, it can be something like a. If I type the word agent of shield and put it in the libraries, it can be split into this form. Okay, it's gonna be agent, which is one word, and split it one by one in each alphabet. It's gonna be AGENTS, and then this phase, agent of shield, or it's gonna be the compound word, or it can be code in the past, like imagination is better than knowledge. For example, those kind of phase or code that people commonly search gonna come with some special characters. Either it's gonna have dot inside in between, it's gonna have space between each word, or it's gonna have like annotation mark, question mark, hyphen, underscore, for example, and those gonna be kind of noise in your wording input. However, in English, it's gonna be pretty simple because you can split it as like one character to each another, and then you need to construct it no matter what is gonna be special characters, or it's gonna be alphabet in English. In this assignment, we didn't care about the uppercase and lowercase yet, so that's one you can skip it. Okay, that's gonna be a little bit difficult to do the comparison in C, but anyway, yeah, that's the ideas that I would like you to be able to make the pseudocode or flowchart to be able to construct the tree structure for fast retrieval, like Google search box, for the alphabet that already came as this kind of input. Like each alphabet has been split one by one into linked list and feed in as input to your system. Okay, to your algorithm, sorry. And then in the end, your pseudocode should be able to show, or your flowchart should be able to show that it has feasibilities that can construct the tree like this from now. If I input a lot of vocabulary in this format, if I input a lot of vocabulary in this format, it should be able to construct it into the tree on the left hand side. Okay, yeah, that's the assignment for today. And again, I'm gonna provide you 1 week to do this assignment. It's not gonna take that long time to implement it, I think, because I'm asking you to do it in pseudocode and flowchart only. Okay, please submit it in LEB2 and see you again on next video. Bye bye.